Wow.
Get your haircut.
Did
It was nice.
Thank you. You got a haircut? I did. Looks good. Thanks.
once the hair like gets into my ears, it bothers me.
Oh, so you can't have long hair then, huh?
It's really hard for me to. I've tried your look before. It's just, yeah, it's tough. My wife actually likes it when my hair's long. It gets shovels. Takes a long time to dry. Oh yeah. Hair's fun. It's just yeah. My ears, I think my maybe ears are sensitive. So maybe there's an issue. All right, it's 4 o'clock. Let's go and get started. Good afternoon, everyone. How's everyone doing today? Good, good. All right, so it's Wednesday, so it's our second meeting this week, and so we should be able to finish up upper extremity stuff today without any issues. And so I have three more examples to do, and then we're going to talk a little bit about injuries, and then we'll go ahead and wrap it up for upper extremity. Okay. All right, and so I think that's all my announcements. Not much to really talk about. Are there any questions I can answer before we get started? Okay. All right, so let's go ahead and pick where we left off. So these are all the learning objectives that we had last time, but we've already kind of talked about quite a few of these, and so we're just going to kind of continue where we left. We can then switch back to the iPad. Okay. All right, so this is the example we kind of stopped at last time. Okay? And so the last class we spent quite a bit of time with the first example we did, which is just kind of a very basic kind of, it's basically someone doing a dumbbell curl, right? And so they're holding kind of a weight in their arm and they are holding and supporting. Okay? And so we saw what would happen if that motion were just supported by a single muscle. But we talked about last time is in reality, you don't. Whenever you go about emotion, even the simplest emotions, it's usually not just one. It's not all put on one muscle, right? It's usually kind of several muscles in your body working together to kind of support that action. And there's a lot of good reasons for that. There's a lot of good reasons why there's a lot of redundancy in your body, which we'll talk about kind of later today. Okay. And so what we started on Monday was this kind of expanded example where we're doing the exact same motion, and so we have someone that has their elbow in kind of a 90-degree angle. They're holding a weight in their hand, but now we're going to see the effect of what happens if we have 3 muscles working on this, except for just one. Okay. And so the 3 muscles that are in your arm are the biceps brachii, the brachialis, and the brachioradialis. And so we're going to try to compute all 3 of these muscle forces in this. Okay. And so this is kind of the configuration that we're working on. Okay. So each of the muscles has their own magnitude, FM1, FM2, FM3, all of which we are going to try to solve in this problem. And all 3 muscles have their attachment ankles given as well. So that's theta M1, theta M2, theta M2. Okay. So we're going to assume that all the geometric properties are known. So theta M1, theta M2, theta M3 are all known, as well as their attachment distances. Okay. So here we have MM1, MM2, 3. Okay. So we're going to assume all those geometric properties are. And so that includes the total length of the arm as well. So the total length of the arm is given by LA. Okay. And we're also going to assume that the arm itself has a weight WA that we're going to factor into our calculations. That's this one. Okay. Okay. And so what we kind of left off talking about last time was that we have 5 unknowns that we want to solve. So we want to solve for all 3 muscle forces, FM1, FM2, FM3. But we also need to compute the reaction forces joints, JX and JY. Okay. And so that gives us 5 unknowns that we need to solve for. The problem here is that we only have 3 equations that we can form just based on, a sum of the forces and the sum of the moments. Okay. And so if we sum up all the forces in the x direction, set it equal to 0, that's going to be one equation. Sum of all the forces in the y direction, set equal to 0 is the second equation, and some of the moments around the elbow is also going to be an equation as well. Okay. So let's actually just write these expressions out, just so that we have. Okay. We're going to need more information than this, but we can at least start with this so that we can at least start solving this. And actually, let me go ahead and draw kind of a bigger version of our figure here, just to kind of make it a bit more clear. Okay. All right. So here I'm going to draw the free body diagram. Okay, so let's start with all the known quantities. And so we know that at the very end of this, at the very right-hand side of this arm, we have a weight that's going downwards. Okay. We have that weight there. And we also have the weight of the arm itself, which we call WA. Okay. And remember, we're assuming that the weight of the arm is acting kind of at the midpoint of the arm, so halfway in. And so the entire length of the arm is given by LA. Okay. And then WA is acting halfway down. So the moment arm for WA is going to be LA over 2. Okay. All right. Then from there, we have all the muscle forces. So we have FM1. And that's acting at a angle of theta M1 relative to the arm itself. Okay. Next, we have FM2, and that's acting at an angle of theta M2. And finally, we have FM3, that's acting at an angle of theta M. Okay. And the distances for all these are given as well. So we know this right here is LM1. This distance right here is LM2. And this distance right here is LM3. And so the last component that we need here, or at least that's not present in the diagram yet, is the joint reaction forces. And so we're going to have a JX acting on the elbow joint horizontally like that. And we're going to have a JY reaction force acting vertically at the elbow joint, just like that. Okay. Okay, and so from this figure here, just because the previous figures that I drew were a little bit kind of messy, and I had different numbers on different figures or different variables, and so I think this kind of makes it a bit more. Okay, so let's go ahead and sum up all the forces. All right, so for all the forces in the x direction, we actually have quite a few forces here. So we have I count 7. So we have JX, JY, the 3 muscle forces, and the 2 weights. Okay, and we need to see which ones are acting in the x direction, or at least have a component in the x direction, right? And so let's just go from left to right. And so the first force that we see in the x direction is JX. and it's acting completely in the X direction, so we can just kind of leave it just by itself. All right, then we have the horizontal component of FM1, and so FM1, we can see here that it's pointing at an angle, and so it's not completely in the horizontal direction, but it is going to have a component in that direction. And so that component is going to be FM1 times cosine of the cosine theta. We're going to write the exact same thing for FM2. So FM2 is going to be a minus FM2 cosine theta M2. And then finally, the same thing for FM3. Okay. So notice that I put minus signs in all these because if you look at the way that the force vector is drawn, you can see that their horizontal component is going to be going to the left. Okay. And if we assume that the positive x direction is going to the right, just kind of as it normally is in the standard form, then if it's pointing to the left, then it has a minus. Okay. All right. And so that kind of brings up an important point. Okay. And so when you're making these kind of free body diagrams and you're doing these force balances and equations of motion, there's lots of different correct ways to do this. And the most important thing is to just kind of be consistent with kind of what you do. Okay. And so what I usually like to do is I'm very much a visual person, and so I go just kind of based off the visual that I see in terms of the image. And so from the FMs, I can see that they're all pointed, to the left. Okay. But another way you could do this, you can put all positive signs in front of those, but then kind of account for those kind of later on in the equation, just because of other things. Okay. And so, my advice to you guys is that, for at least for me, I go off the visuals. And so, if you see an arrow is pointing in a particular direction, at least the way that you drew it, then kind of keep that same direction in your equations. But if you have another way of doing this, that's typically how I do. Okay, so that's our x equation, and so our x equation has 4 components to it, and then that's that. Okay, now let's look at the forces in the y direction. Okay, so the first force we have in the y direction is jy, and jy is pointed vertically upwards, and so we're going to have a positive sign there. Then we have all the components due to the muscle forces, and so I'm just going to kind of go through this kind of fairly quickly. And so when you want the vertical component of a vector, and the angle that we're given here is with respect to the horizontal, we want to take the sine of that angle, right? So FM1 sine of theta M. Okay. We're going to do that for all of the angles. Okay. FM2 sine of theta M2 plus FM3 sine of theta M. Okay. And then once again, I wrote all these terms with a positive sign in front of them, because the way that these vectors are drawn, the FM vector right here, you can see that its vertical component is pointing upwards. Okay. That's why we put a positive sign. All right, and then finally we have the 2 weights. And so I got this question yesterday, and so whenever we're considering the weights of an object or an external force or the weight of a body segment, we always assume that the weight is pointing vertically downwards. So we're going to assume that Earth is kind of just vertically down, and so any kind of weights are kind of point in that direction. Okay. And so I think the question came up because we were looking at a homework problem, where the elbow was kind of bent at an angle like this. Okay. I believe kind of the angle that I gave you was this. Okay. And so a very similar situation to what we did in the class, except that we're kind of angling the elbow downwards. Okay. And so just like in class, we had 2 weights to consider. And so we had the weight of an object that's being held in the hand, and we had the weight of the arm itself. Okay. But even though the elbow is bent here, we assume that the weights are kind of pointing vertically downwards. That's the direction. Okay. Because I think the tempting thing to do here is that, you might say that the weight is acting perpendicular to the arm itself, and so you might put the weight in that direction. But remember, the weights are always vertically down. We always assume that gravity is pointing vertically down. It's just. Oh. So that's why whenever you have any weights, unless we're summing up the forces in kind of a strange direction, which we're actually going to do an example of that later today, you can always assume weights are kind of vertically downwards. Okay, and then finally we have the moment equations. And remember, usually what we like to do, just for the sake of simplicity, is we like to sum the moments around the joint, because that will eliminate two of the forces from our equation. Okay, and so here we're going to sum around the elbow joint on the left. And so since we're summing the moments around that elbow joint, Jx and Jy are not going to factor into that equation. Okay, so we're only going to have all the other forces. Okay. So once again, let's go from left to right. So first we have the moment due to Fm1. And so the moment due to Fm1 is going to be the vertical component of the force, or the force that's kind of perpendicular to the line of action. So that's Fm1 theta m1, or excuse me, Fm1 sine of theta m1. And then we multiply that by the distance between that force and the joint. And so it's Fm1 sine of theta m1 multiplied by Lm1. Okay. And I give it a positive sign because this moment is going to produce a counterclockwise moment around hence it has to be positive. Okay. And so we're going to have very similar expressions for Fm2 and Fm3. Fm2 sine of theta m2 times Lm2 plus Fm3 sine of theta m3 Lm3. Okay. All of those are positive, but they're all producing counterclockwise moments. Okay. All right. And then we have the moments due to the two weights. So we have WA minus WA, LA divided by 2. So WA is already acting in the direction that's perpendicular to the line of action. So we don't have to multiply by any sine or cosine. We just have to multiply by its distance. We have WA times LA divided by 2. It's W, it's LA. All right. And so those are our first three equations for this. Any questions on how we got these equations here? All right. So this is a good start. So we're going to use these equations anyway, but we already kind of knew beforehand that this wasn't going to be enough, right? And so in order to solve for all of the unknowns, we need at least two more equations. We're going to have to get these equations in this company. And so in reality, this is a very common So just like I talked about before, there's a lot of redundancy in your body. You have kind of multiple muscles that kind of all kind of contribute to the same action. Right? Even something as very basic as kind of elbow flexion, you can see here we have muscles. Okay. And so this is not something that's unique to this problem. In fact, it's a problem that if you're going to do any kind of practical calculation, you're going to have this issue. Okay. And so there are multiple approaches to solve this. Okay. I'll tell you, let's start with kind of the more difficult approach, the one that we actually won't be able to do by hand because you need a computer, and then we'll go to one that's kind of difficult. Okay. And so, the kind of the standard way that's dealt with this is to use something called optimization. And I know some of you are in my optimization course. So I'm not trying to plug that course. This is actually what they use. Okay. And so if you're unfamiliar, optimization is basically a way to solve these kinds of systems where you have kind of too many unknowns or too many, what we call in that class, too many design variables and not enough equations. Okay. And so what optimization will do is it'll allow you to kind of come up with these answers that satisfy those equations in the best way possible. But to run an optimization, you need kind of one additional thing, and that's called in optimization we call it an objective function. But here, we need to have some kind of criteria in terms of how we can split the muscles. Okay. And so kind of in a nutshell, kind of what the criteria that's usually used in biomechanics is usually energy efficiency. Okay. And so generally, for almost all biological systems, for humans, for animals, for fish, just in general, right? Usually, the most energy efficient way is usually the best way to do things. Okay. And so if you have a situation like this where you have kind of your body needs to perform an action, your muscles will always act in a way that tries to preserve as much energy as possible. Okay. And so, just to kind of give you an example. So, if you were to try to perform this action and your body made one muscle do all that work, that's not very energy efficient because then you're going to have one muscle that's going to be tired and it's not going to be able to contribute. Okay. And so the best thing would be is to kind of split that work up, in terms of energy efficiency. Okay. But in order to solve these equations, you basically need a computer to do it. Okay. And so whenever you run optimization, at least in any kind of practical way, a computer is needed to kind of solve all of those equations simultaneously. But a lot of biomechanics problems are actually solved computation just due to the complexity of the geometry, due to the complexity of the systems. And so something like this is usually readily available. And I'm gonna try really hard this semester to get there. But last year when I taught this, I wasn't able to get there. But there is a software that I've been kind of experimenting with in terms of human motion biomechanics called OpenSim. And I've written up some tutorials about it, and so it's able to do something like this. And so I'm hoping that we can get to it at the end of the semester. But if not, I'll give you guys all the materials. And the good thing is that it's an open source software, so you can kind of play around with it as just fun. Okay. But if you don't have a computer, what's one way that you can solve this problem? Well, one way that we can solve this problem is that we can make assumptions. And so in particular, we're going to make assumptions based on the relative amount of force or the relative strength of each muscle kind of compared to one another. Okay. And so when you have kind of, multiple muscles kind of contributing to a single action like this, each one is going to contribute a different amount of force, right? Because each muscle is different, right? So they have a different different geometry, different length, different amount of muscle fibers, okay, and all those different things. Okay, and so there's lots of ways that we can do this, but I think kind of the easiest way is just to go based purely on the size of the muscle. In particular, we're going to look at the cross-sectional area of the muscle. And so, in other words, we're going to make a proportionality assumption like this. So what we're going to say is that FM1, the ratio of FM1 to FM2, or in other words, the ratio of the amount of force that the first muscle can exert compared to the second muscle is going to be proportional to their cross-sectional areas. Okay. So A1 and A2 are the cross-sectional areas of those muscles. So bigger muscles can exert more force, right? So when you say it makes sense. But there's a lot of kind of biological backings for this as well. Right? So remember when we talked about muscle biomechanics a few weeks ago, we talked about the fact that muscles are kind of comprised of these sarcomeres or muscle fibers. Okay? And I think someone asked the question about this, but generally the more muscle fibers or that you have in parallel in a muscle, in other words, the wider your muscle is, the more muscle fibers that you have to kind of contribute to the motion. So it makes sense. Okay. And so this seems like a kind of a fairly basic way to kind of do it, but there's it checks out. It makes a lot of sense. Okay. All right. And another good reason for this assumption is that the cross-sectional areas for the muscles is usually not difficult to obtain too. And so even though your body has kind of a complex network of muscles that kind of overlap each other, if you have the right kind of measurement equipment, if you have kind of a scanner, or even you can even do it externally with certain instruments, you can actually measure the cross-sectional area of a muscle with relatively good accuracy. So this is not, this is not something we're just making up just to help us solve this problem. This you can actually do this in practice. Okay. All right, and so the good thing is that this equation here that I boxed, this counts as an equation. So if we call this equation 4, and maybe we can just make one more equation here. So we have maybe FM1 divided by FM3 equal to the ratio of their areas, A1 over A3. This could be a fifth equation, okay? And so together with the 3 equations that we had before, based on the equations, motions, and our force balances, we're able to use all 5 of these to solve this. Okay. I'll let you guys kind of fill in the rest. Actually, in fact, you have to because it's one of the homework problems. And so I think it's problem 3 or something on the homework that has you do this. Okay. But the way that you would do this is that you can use both these equations. You can solve for FM2 here. Solve for FM2. You can solve equation 5 for FM3. Right, so then you'll have explicit expressions for the muscle force 2 and 3, and then what you can then do is you can plug this back into equation 3. Plug these back into equation 3, because if you look at equation 3 here, equation 3 only had FM1, 2, and 3, so it doesn't have JX and JY. And so if you plug in the expressions for FM2, FM3 there, you'll have just one unknown in that equation, which is FM1, and you can solve for it. And so if you're kind of a little bit stumped on how to get started with that one, that's generally how I would solve it. And then once you have FM1, then you can solve for FM2, FM3, and then use those and solve for JX and JY. Okay. So it's a lot of algebra. Okay, so I'm not even though I'm maybe I'm making it seem easier than it is, and so it is a lot of algebra. It's a lot of plugging in. It's not the most exciting thing in the world, but that's generally how I would approach that problem. Okay. Any questions on this example here? All right, and so that's that's generally what you would do when you have more muscles than you have equations. So let's look at another joint. Okay, so we spent all this time talking about the elbow joints. Let's look at another joint. So in particular, let's look at the shoulder joint, which is I think the most interesting joint in the upper extremity. And so just like we mentioned on Monday, the shoulder joint is very fascinating because it has such a wide range of motion. Okay, so it's more than just flexion and extension. We have kind of abduction, adduction, rotation, all these different things. Okay. And so to support all these different motions, the shoulder joint is actually acted upon by quite a few muscles. And so the first example and the one that we're actually going to do calculations for are the deltoids. So the deltoid muscles are the muscles that are kind of right on top of your shoulder. So when you put your hand on your shoulder, when you're putting your hands basically on your deltoid. Okay. So your deltoids are primarily responsible for shoulder abduction. So basically bringing your arm away from your body. Right. Another muscle that acts primarily as your muscle is the latissimus dorsi, which I don't have in front of me, so I'm going to misspell it, but usually people just call them the lats. Okay, so your lats are the kind of the muscles in the upper kind of your upper back, kind of right on top of your scapula. Okay. Right, so the latissimus dorsi is primarily responsible for shoulder flexion. So any kind of pulling motion that kind of where you pull kind of your arm backwards, that's your latissimus dorsi. And then you also have your there's others, but we'll do kind of the opposite of the latissimus dorsi, which is your pectoralis, which is responsible for shoulder extension. Okay. So lots of different muscles, for lots of different things. And even if we were to do kind of a very thorough analysis of the shoulder, we'd have to do it in 3 dimensions because it has such a wide range of motion. You'd have to account for all 3 of those, all 3 directions, X, Y. We're not going to do that just because of kind of time restrictions. But I did kind of want to highlight that to you. Okay. But the example that we are going to do is we're going to focus on just one muscle. We're going to focus primarily on the deltoids. So for this example, let's consider an arm that kind of fully extended. And just like the previous example, we're going to assume that we're holding a weight at the very end of the arm. So the example looks like this. You're going to be seeing lots of boxes in this class because that's just the generic weight symbol I have. It's just a box. Okay. Okay. And so this is going to look actually quite similar to our previous examples, except that we have kind of an extra body segment there to take into account. Okay. All right. And so the primary muscle that we're going to be looking at here is the deltoid. Okay. So the deltoid has a muscle force that's pointing in that direction. Okay. And just like we usually do in these examples, we're going to assume that we know the distance on where it attaches. This we'll call this LM. And we also know the attachment angle theta. And so in addition to that, we are given the two lengths of the arm. And so we have the length of just the upper arm itself, and so we'll call this LA. And then we have the length of the entire arm, so that's the length of both the upper and the lower arm. We'll call that L. All right. And so in addition to the muscle force, we're going to have the joint reaction forces. And so we have JX and JY. Okay. And just like in the previous example, we're going to solve for all of the unknowns. So compute. Or in this case, I don't give you any numbers. So let's just come up with expressions for JX, JY, and F. All right. So fairly simple example. So we're going to go through this very quickly, but I bring this up just kind of for a couple of reasons. So the first thing that probably some of you are wondering is what about the elbow joint, right? And so this weight here is being held kind of more distally to the elbow joint, and so the question is, do we kind of consider anything that's happening at that joint right here? So in reality, yes, there are forces that are being applied at that joint to kind of hold this in static equilibrium. But whenever we do these analyses, we kind of look at the system as a whole. Okay? And so yes, there are internal forces that are acting on the system, but we just consider them to be kind of internal forces. We don't consider them part of the calculations. Okay? Same thing for the muscle forces on the inside too. And so, if you're going to holding your arm out extended like this, it's likely that your biceps muscles are going to be doing a little bit of work too. But we're mostly just concerned with just the deltoid muscles. And so for any kind of muscles or joints that are kind of internal to the geometry that's being considered, usually we just kind of neglect them. We just say they're kind of acting internally. Okay. That's definitely an assumption. And so it's an assumption we have to make. And the way that we've kind of drawn this here, it's going to make it seem like the deltoid is doing a lot of work. But once again, that the amount of force that we're to compute here is an overestimation of what's actually being done, because in reality the shoulder has other muscles to kind of help with that. Okay. All right. Another point I want to bring up is the directions I chose for JX and JY. Okay, we haven't really talked about those yet. Okay. And so when you're adding the reaction forces to a free body diagram like this, it doesn't really matter all that much kind of what directions that you put them in. The only thing that you have to do is you have to be consistent with that in your equations. Okay. And so usually what I like to do when I draw the reaction forces, and I draw them in the positive x direction and the positive y. Okay. That way, when I kind of when they show up in my equations, in the fx and the fy equations, they just show up as kind of positive terms. Okay. But we're not making a statement, so we're not saying that we know for sure that the reaction forces are actually going to go in the directions that we state. It's just kind of there for mathematical kind of convenience. Okay. But then sometimes what you'll see is that after you assign the reaction forces and after you solve everything, you may find that the reaction force that you get is actually going to be negative. And so if you get a negative reaction force from your calculations, all that means is that the actual direction of the reaction force is opposite of what. So technically that's true of the muscle force too, but if you're getting kind of a muscle force that's acting in the opposite direction, probably you should check your work because remember muscles can only act in tension. Okay. So I'm just going to kind of fly through this example here just because it's pretty fast. But let's go ahead and sum up the forces in the x direction, sum up the forces in the y direction, and sum up the moments. Okay. And in this case, the joint of interest is the shoulder joint, and so we're going to sum up the forces around the shoulder joint. Okay. All right, and so if we sum up the forces in the x direction, we set it equal to 0. This is jx minus fm cosine theta m. Okay. Sum up the forces in the y direction, we have jy plus fm sine of theta m minus wk w. And then we sum up the moments around the shoulder. This gives us fm sine of theta m lm minus wa a minus w l. Okay. All right. So I'm just going to solve this last equation here for fm because fm is the only unknown in that equation. Okay. And so if we solve for fm, we add WALA to both sides, add WLW to both sides, divide by sine of theta m lm. What we get is fm is equal to WALA plus W divided by lm sine of theta. So very, very similar result to the first example we did Wednesday or on Monday, with one kind of important difference. Kind of the big reason why I kind of brought up this example. All right, and so if we look at that term in the denominator, we have sine of theta m, right? And so let's do kind of a similar analysis that we did on Monday, where we compute or we see how the value of Fm is going to change relative to theta m. All right, so let's first look at the effect when theta m gets small. So when theta m basically approaches 0. And so geometrically, what's happening is that as theta m gets smaller, the muscle force kind of points more and more and more parallel to the limb itself. And so we go back to the free body diagram kind of really quick right here, okay? And so you can see as theta m here gets smaller, Fm is going to go kind of more closer and closer to that. Right, and so the extreme, of course, is if theta m is equal to 0, and if theta m is equal to 0, then Fm just kind of points parallel to the arm. Mathematically, what happens is that when theta m goes closer to 0, right? What's sine of 0? Sine of 0 is 0. Right? And generally speaking, sine of an angle gets smaller as the angle gets smaller as well. And if sine of theta m gets smaller, then what that does is makes Fm larger. So that's an important trend, right? And so as the attachment angle for muscle kind of gets smaller and smaller, it's going to require your muscle to apply more force in order to perform actions. Okay. Right, and that makes sense, right? And so remember, a lot of the motion that the human body does is really primarily due to force that your muscles produce around your joints. Okay, and so any factor that makes it more difficult to apply that torque, for the muscle to apply torque on a joint, is going to cause the muscle to work harder in order to produce the same amount of motion, the same amount of torque. And the attachment angle is pretty big. So this is kind of a common theme that we'll kind of come back in modern later sections. All right. Any questions on this? Okay. And so for this section, I'm doing a lot of this where we're solving these equations according to the variables, and we're kind of doing a lot of analysis in terms of how does each of these variables affect our solution. So a lot of biomechanics is like this, because what you'll kind of learn very quickly is that even though I've kind of been saying that biomechanics is just mechanics, right? The fact that you do have very complicated geometries, you have some overdetermined, you have some underdetermined systems, too many muscle forces and not enough equations. A lot of times you kind of have to rely on kind of trends and kind of heuristics. Okay. And so when you solve, systems like this, which this obviously is a very simplified version of what's actually happening in your shoulder when you're extending it like that. Even though something like this, you're not able to get kind of quantitative results where you can plug in numbers and say, yeah, that's the exact muscle force that deltoid is going to do, right? That's hard to kind of justify with such a simple geometry. But what you can do is that you can take your results and you can draw trends. And so what you can say is that, all right, this equation right here may not give us an exact answer for the deltoid muscle force, but it'll at least tell us. And so for patients or for people that have certain attachment angles where, the attachment angle is greater than some others, that can give you some hints in terms of, this person's deltoids are going to work harder than this other person's just based purely on their anatomy, just based purely on their geometry. Okay. So that's why, I'm kind of spending a lot of time highlighting these kinds of trends, because, these are the kinds of things that can kind of bring, when you're designing, let's say, like a device that attaches someone, maybe you can, as a doctor, you can tell that, maybe a device will be more useful for this person, just based on their kind of muscle anatomy, just based on their bones. Okay. All right. Okay. So this next example here, I'm not going to take it all the way, just because I do want to talk about injuries today. But I think it is kind of important just for the homework. I've already got a few kind of questions. Okay. So for this example here, we're going to look at the shoulder joint again, but we're going to look at the shoulder joint kind of being angled instead of being straight out. This, so we have the shoulder joint up there. All right, so same thing as before, we have a weight that's being applied at the end, okay? But now the shoulders are kind of, lowered by a certain thing. All right, and so to characterize the kind of how much the arms are bending downwards, I'm going to give you this angle right here. Okay. This is like the armpit. So the angle that you measure just based on the person's armpit, so we'll call it theta A. All right, so just like before, we're going to consider just a single muscle, and so we're going to consider the deltoid muscle. Okay, so we'll call that theta FM. And we'll say that we know the attachment angle. The attachment angle is theta M. Okay. And then just like before, we're going to have the weights of the objects. And so we're going to have the weight of the arm, WA, the weight of the weight, which is W. Okay. And just like in the last problem, we're going to have all these lengths. So we're going to have this length right here, which is LA. The length over there is going to be L. Okay. All right. Lastly, we need the joint reaction forces, and so just for simplicity, let me go ahead and draw them in X and Y directions. Okay, so we have JX and JY. All right, and so just like we did before, we're going to compute FM, JX, and JY. All right. And so this looks like, this looks very similar to the problem that we did before, but what you'll see is that the fact that the arm is lowered is actually going to, cause a lot of differences in our calculations. Okay. All right, question. So will the joint reaction forces ever be at an angle? So yes, you can. So actually in the notes, I do have the joint reaction forces acting at an angle. And so I have the joint reaction force, one that's kind of going parallel to the arm, and I have one reaction force that's going perpendicular to the arm as well. So you can do that, and so that's a totally valid thing to do when you're kind of doing these problems. It's just kind of all a matter of convenience, and so usually if you're going to do that, if you're going to have the reaction forces at an angle, usually it kind of makes more sense to sum the forces in those directions. Which in the past, Justin, so me in the past would say that's the more convenient way to do this problem. But recently I've been kind of just saying that let's just do some of the forces in the X and the Y direction, and then we'll adjust based on the trigonometry from there. So it's just a matter of preference, and so if you prefer to angle the reaction forces in that direction, that's fine too. you're actually going to get the same result. The magnitude of the force should still be the same, and the ultimate direction of the reaction force should still be the same as well. It's just kind of how you characterize it in terms of the initial vectors. Yeah. Okay. All right. So we're gonna have our force balances. Okay. But for this problem, just kind of for the sake of time, I'm just going to do one one equation here, which is the sum of the moments. Okay. So the moment equation is almost always a good one to start with, because the moment equation, if you kind of formulate it correctly, is not going to have the joint reaction force. So you're usually going to have just one equation for the one unknown, which is Fm, and that's usually a good place to start. Okay. All right. And so to do this, actually, let me go ahead and draw the geometry again. For this length right here, A, this right here is L. The total length is LW. Okay. We have Fm acting that way, beta M, and this length is L. Okay. So I just kind of drew it again just to be kind of clear. Okay. All right. And so the way that we compute the moment equation, we're still going to use the same logic, but we're going to have to make some adjustments based on the fact that our arm is angled. Okay. Let's start with Fm. All right. And so just visually, what we can see here, that Fm is going to produce a counterclockwise moment around the shoulder. Okay. And so we know for sure that it's going to be a positive moment. Then what we're going to do is we're going to take the component that's kind of perpendicular to the line of action. Okay. So the line of action is kind of what I highlighted there in orange. Okay, so that's the shortest distance between the force vector and the joint. Okay. And the component that's kind of perpendicular to this is going to be kind of at this angle right here. Okay. Okay. And so it looks kind of like a strange angle here, but we kind of draw this triangle right here. Okay. And so let me kind of bring this up here just to give it. Okay, so we have Fm, this. We have a direction that's kind of perpendicular to this. So it's kind of like this. And a direction that's parallel to this. Okay. This component right here is perpendicular to the arm. And this component right here is parallel. This angle right here is theta. All right. So the component of the force that we want is actually perpendicular to the, because that's the one that's actually going to produce the moment. Okay. Any force component that's kind of parallel to the limb that you're considering is not going to produce any moment, because it's just going to point straight at the joint. Okay. And so the component that's perpendicular to this is going to be Fm. Fm is the hypotenuse of this triangle, and then we want the component that's kind of opposite of this theta here, which is sine of theta. Okay. So we have sine Fm, sine of theta m, multiplied by Ln. Any questions on how I got that expression there for the moment from Fm? All right, so now let's look at the moments from WA and W. Okay. And then once again, I'm going to draw triangles here to kind of illustrate, what these look like. Okay. All right. Kind of question. So the line of action is always going to be the arm. So the line of action is remember what we said was the shortest distance between your force vector and the and whatever axis that you're rotating around. Okay. And so it's going to be a little bit different for WA and W. So let me go ahead and illustrate that here. Okay. So for WA, we're going to be looking at this right here. Okay. If we're to kind of isolate this, we have the shoulder joint. And then we have WA, which is acting down here. If we were to kind of complete this triangle, and so we have kind of the direct line from the shoulder joint to WA along the arm, and this is the length that we're actually given. So we know that this length here is LA. Okay. If we were to draw a triangle like this, right? We know what this angle is, right? This is the armpit angle. So this is theta A right here. Okay. And so what we want to find out is, what's the moment arm, what's the lever arm for this WA? Okay. All right. And so in this case, it's not actually going to be LA itself, okay? Because this WA is kind of acting in just kind of the purely vertical direction. And so for these cases, what I usually like to do is, that vector, we kind of drew it in that certain way, acting at that point, kind of arbitrarily, right? If we were to kind of extend this vector in this direction, okay, just like that, right? From here, it's a lot more easy to determine, what's kind of the shortest distance, right? So that's the line of action. That's the moment arm that you want to compute. Is what's the shortest distance between this vector and the joint. Okay. And so in this case, when we draw the line up like this, we can see that the shortest distance is actually this distance right here. Because this distance right here, this will be perpendicular to the force vector. Okay. And this is the distance that we want to multiply by by W to get its moment. And we can determine what that distance is just based on trigonometry. Okay, so we have the hypotenuse of that triangle, which is LA. And if we look, this purple line is exactly the same length as this line right here. Okay. And so based on trigonometry, the length of that line is going to be LA sine of theta A. Okay. And so the moment from that WA is therefore going to be WA minus sine, because we know the WA is going to produce a clockwise moment around the joint. Okay. WA times LA sine of theta A. All right, so that's kind of two different ways to kind of determine how to get these moment terms. So one way that you can look at it is you can find the component of the force that's perpendicular to the line of action and multiply that. Another way that you can do it is you can kind of extend the vector outwards and find out what the shortest distance between that vector is to the joint. Okay. Both methods work, and I'm showing you both here just to kind of just so that you kind of see what makes the most sense to you. All right, any questions on that? Okay, and so if we look at W. Oh, sorry, that was one. Okay, and so if we look at the force W here, you know, it's very similar to the WA, and that's acting vertically downwards. Okay, and so we can use the same you know, the same logic here to say that the moment due to the weight W is minus W LW sine of theta. And all of that's going to be equal to question. So we could have broken up LM instead of FM and still get the same answer. Yes. Yes, you could have. It's kind of like pick your trigonometric poison. So yeah. So I think, you know, the way people see geometry and the way people see trig is kind of a little bit different for everyone. I think it kind of depends on kind of how you learned it. And so, you know, whichever way kind of makes the most sense to you, you know, I would go for it. I think, you know, for this part of the class right here, and you know, this is primarily the calculations that we're going to do for the first midterm. I think just the concept of everything is not that difficult for people, but the geometry and the trig is actually very challenging, which I think people don't expect. But that's you know, that's biomechanics, right? And so the concepts aren't hard, the geometry is what's hard. Okay. All right, and so the good thing about this expression here is that, you know, we only have one unknown, and so the only unknown in this equation is FM. Okay. Usually, you know, like I mentioned before, all the geometric qualities I'll give to you. So that's the lengths, the angles will be given to you, all the external forces, the weights I'll give to you too. And so you can solve this expression for FM, and then you can use that FM to solve for the joint reaction forces. All right, any final questions on this example? Okay, all right, and so if you look at the lecture notes, and so if you look at lecture note 06B, you know, I did finish this example. You know, I'm not going to leave you hanging like this, and so you'll be able to see kind of the entire kind of process of computing the reaction forces. But with the last 5 minutes of class today, I did want to jump back to the slides because I wanted to talk very briefly about kind of common injuries of the upper extremity. Okay. And so I have kind of 3 slides I'll just kind of go over very, very quickly for the last couple minutes. Okay. So let's talk about common injuries at the shoulder. Okay. And so just like I mentioned before, you know, probably the most common dislocation that occurs in the human body is the shoulder dislocation. Okay. And that's just due to the fact that, you know, this joint right here is just very flexible and very loose, just naturally. Okay. And so when you have shoulder dislocations, it can happen in a lot of different ways. And so the most common ways are anterior and posterior dislocations. So those are dislocations that occur in the front and the back of the body. Okay. Another common way is inferior dislocation, which is dislocation where your shoulder kind of gets pulled downwards. Okay. The only direction where dislocations are not common is superior. So, you know, it's very uncommon for your shoulder to kind of dislocate upwards towards your head. Mostly just kind of based on the geometry and the strength of the ligaments. Okay. And the unfortunate thing is that if you've had dislocations before, you know, it kind of puts you at risk for more dislocations in the future because your ligaments get weaker, your tendons get weaker in that area just because they're kind of stretched kind of beyond what they're used to. Okay. Another common injury at the shoulder are rotator cuff injuries. And so these are actually very common for baseball players because baseball players, they end up throwing, you know, balls a lot. So, you know, any kind of overhead or rotation motions of the arm that you're kind of doing excessively is going to hurt your rotator. Okay. And by rotator, the rotator cuff is kind of a generic term that refers to all the ligaments and tendons and muscles kind of around the shoulder area. Okay. So your rotator cuff is not specifically one ligament or it's not specifically one muscle. It's just kind of all the muscles kind of in ligaments and tendons in that area. All right. So elbow injury. So elbow is actually not that commonly injured. It's a pretty stable joint. And so because it's stable, you don't get a lot of injuries there. And so what you actually see a lot are what's called overuse injuries, where you kind of subject your elbow to lots of repeated movements, which can cause like a stress fracture or kind of a stress stress reaction. Okay. So one common example for this is an injury called tennis elbow, which occurs for people who like to play tennis a lot. Okay, and so the scientific name for this is called epicondylitis. Okay, and so this involves kind of a lot of kind of damage to the ligaments and tendons in that area, because whenever you kind of swing a racket, you kind of put a lot of kind of lateral stress on your elbow. Okay. You can dislocate your elbow too. That's possible, but it's kind of rare. It doesn't happen that often. All right, and then finally we have wrist injuries. So wrist injuries are actually becoming more and more common because your wrist is kind of involved in kind of a lot of daily activities that we don't really think about. So things like typing on a keyboard, typing on a phone, handshaking someone, writing with a pencil, right? Your wrist is subject actually to quite a lot of stress, not extreme stress in the way that an athlete would, but a lot of kind of repeated movements that kind of put a lot of kind of stress on the wrist. Okay, and so one injury that's actually becoming quite common, and I think there's just a lot of people kind of have it to a certain degree nowadays, is carpal tunnel syndrome. So carpal tunnel, you've probably heard the term before. It's not an acute injury, and so it's not like you're tearing the ligaments or you're tearing the tendons or you're not tearing the muscles. It's none of that. The carpal tunnel is actually a nerve injury. So you have this kind of very large nerve that kind of runs through your hand called the median nerve. Okay, and what tends to happen is that if you kind of type in a strange way where you're kind of putting a lot of pressure on that nerve can actually become pinched, and so kind of the tissue around that area swells up, and it pinches that nerve, and that's kind of what causes that kind of pain and kind of tingling sensation that you have in your hand. That people associate with carpal. And so, I would say carpal tunnel is actually one of the hottest areas of research right now, because a lot of people are getting it more nowadays because you have a lot more people kind of sitting at their desk, kind of typing in like not the great posture. You have people that are using their phones a lot. You have people that are writing a lot. So, it's definitely becoming a much bigger issue nowadays. And I think especially as kind of our generation gets older, we kind of grew up, typing on keyboards when we were little. I think you're going to see a lot more carpal tunnel syndrome. Okay. All right, any final questions before we wrap it up? I know I kind of speed ran through the injuries, but hopefully that kind of gave you a good sense of that. Okay, all right, and so that's all we got time for this week. So thank you guys for coming. For next week, when we pick it up again, we're going to talk about the lower extremity. So that's the hip, your legs, your feet. So another very interesting area of the body, and so I'm guys looking forward to that. So thank you guys for coming. Hope you guys enjoy the rest of your weekend, and I will see you on Monday. Thanks.
Very kind of written.
Well, any final questions from Zoom? All right, I will see you next week.